In its natural state, electricity is chaotic. A lightning strike violently fractures the atmosphere, discharging tens of thousands of amperes in an unpredictable, branching web. Harnessing this raw power required taming that unpredictable burst into a smooth, continuous path. This creates a steady electric current. It occurs when a net amount of charge flows uniformly over time, much like water moving down a riverbed. In its simplest form, you route this current through a basic circuit, a single closed loop containing one power source and one resistor. You can calculate the exact flow here using Ohm's law, which states that voltage equals current multiplied by resistance. But a single loop only provides so much utility. To build more capable devices, engineers rapidly pushed beyond simple, solitary pathways. As electrical designs matured, those single loops expanded into dense, intersecting webs of wire. Initially, you can simplify these webs. If components are placed one after another in a series, or branched side by side in parallel, standard algebraic rules allow you to collapse them into a single equivalent resistance. Looking at this complex multi-loop circuit, we hit a strict mathematical wall. When a network contains multiple intersecting loops and power sources arranged in complex topologies, the standard reduction rules fail. The exact point of failure occurs when batteries sit in opposing branches of the network. The currents push against each other, meaning you can no longer simply add the voltages together algebraically. This creates a severe engineering problem. How do you calculate the precise current and voltage across a specific wire when the network's geometry prevents any basic simplification? Solving this requires discarding the analogy of water flowing through simple pipes. You need a rigorously algorithmic approach. To decipher the flow within an irreducible circuit, we have to look past the individual wires and apply the absolute physical laws that govern the space they occupy. In the mid-19th century, a German physicist named Gustav Robert Kirchhoff provided the solution. Working as a professor in Heidelberg, Kirchhoff focused deeply on mathematical physics. He recognized that electrical networks were entirely predictable if you anchored them to the laws of thermodynamics. A circuit is a physical space where energy and matter interact. That means the entire system is strictly bound by macroscopic conservation laws. To map this mathematically, you start with a strict prerequisite. Before calculating anything, every branch in the diagram must be assigned a theoretical current variable, denoted as I, and an arbitrary directional arrow. Kirchhoff took the grand thermodynamic principles of the universe and translated them into two highly practical operational rules for circuit diagrams. The first of these is universally known as the junction rule. As we see in this diagram of a single node, the rule dictates that at any junction, any point where multiple wires meet, the sum of the currents entering that exact point must equal the sum of the currents leaving it. If a main wire splits into two branches, the mathematical relationship is strict. The incoming current, I3, exactly equals I1 plus I2. This requirement is a direct manifestation of the conservation of charge. In a steady electric current, electrons flow continuously. Because they carry physical charge and mass, they cannot pile up, compress, or vanish at an intersection. The junction rule is the physical guarantee that whatever quantity of charge enters a crossroads must successfully exit it. Kirchhoff's second rule, the loop rule, handles the closed pathways within the network. Tracing this closed circuit path, the rule states that the algebraic sum of changes in potential around any closed loop must equal zero. Think of electric potential as a physical landscape. Moving through the circuit is like hiking over hills, representing the batteries, and through valleys, representing the resistors. When you trace your path across a power source from the negative terminal to the positive terminal, you gain energy. This is recorded mathematically as a positive voltage rise. Conversely, when you move through a resistor in the same direction as the current, energy is dissipated as heat. This creates a voltage drop, written as a negative I times R. By tracing the full path and returning to the exact starting point, all those voltage rises and drops stack into a definitive equation that balances perfectly to zero. You might worry about drawing your initial current arrows in the wrong direction, but the algebra is self-correcting. If solving the equation yields a negative number for a current, it simply means the actual physical flow is in the opposite direction of your drawn arrow. Just as the junction rule enforces the conservation of charge, the loop rule enforces the conservation of energy. Electric potential is strictly tied to physical location. If a charge navigates a maze of wires and returns to its exact starting coordinate, it must possess the exact same potential energy it began with. By tracking charge at the junctions and energy around the loops, Kirchhoff translates the physical chaos of a tangled network into a clean, solvable system of linear equations. We can test the absolute scalability of this framework by moving away from flat diagrams and analyzing a three-dimensional structure. This is a physical cube constructed entirely of 12 identical resistors. If we connect a battery across two diagonally opposite corners, we need to find the total equivalent resistance of the entire structure. There are so many diverging and converging paths here that isolating a simple series or parallel sequence is mathematically impossible. Instead, we apply the junction rule. Because the geometry is perfectly symmetrical, total incoming current splits equally into the three initial diverging edges. We then apply the loop rule, tracing one single continuous path through the outer edges from the entry corner to the exit corner, summing the voltage drops along the way. The equations collapse, revealing the equivalent resistance of these chaotic edges is exactly 5/6 of an individual resistor. Kirchhoff's rules do not care about visual complexity or spatial dimensions. The thermodynamic laws they are built upon scale flawlessly to any geometry. This rigorous scaling is what makes practical electrical engineering possible. A classic example is the Wheatstone bridge. This instrument is used to determine an unknown electrical resistance with extreme precision. This schematic diagram reveals a diamond-shaped network with 4 resistors, bridged through the center by a sensitive current meter called a galvanometer. The operator tunes the known resistors to reach a null point condition. This occurs when absolutely zero current flows through the central bridge. To prove why this works, apply Kirchhoff's loop rule to the 2 closed triangular loops inside the diamond. Because the central current is 0, the loop equations simplify cleanly, revealing a locked ratio, resistance 2 divided by 1 equals 4 divided by 3. This exact ratio allows engineers to calculate the unknown resistor perfectly. It is a measurement technique derived entirely from the absolute truth of Kirchhoff's framework. We can zoom out from antique testing boxes to the scale of modern infrastructure. Whether analyzing the microscopic copper traces of a printed circuit board or balancing a national power grid, the foundational algorithms are Kirchhoff's rules. By anchoring electrical behavior to universal conservation laws, Gustav Kirchhoff established the algorithmic framework used to map, understand, and master the electrical webs powering the modern world.